All right, welcome to this recording of my lecture for the Deep Learning 2 course for the Masters in AI at the University of Amsterdam. This is the first lecture of the course called Self-supervised and Vision Language Learning. And of course, we know self-supervised and vision language learning is everywhere now, notably with GPT-4 making the news. I mean, The Guardian has its own section on ChatGPT related news where ChatGPT, of course, the underlying model GPT-3 was trained using self-supervision, and then all kinds of other things that you've probably seen if you're around on the internet. And in this course, we will cover a bunch of models, a bunch of ideas that these models propose. I will sort of assume all the basic knowledge that we've covered in Deep Learning 1, which includes regularizers, optimizers, deep neural network architectures, what a transformer is, including some loss functions. So this will all be necessary to understand what we're going to cover. The intended learning outcomes of this 2-lecture short course are the following: that the student can present and explain the crucial works in the large-scale vision language learning domain, explain the difference and commonalities between previous and more recent approaches. We will be talking about a technique or a method called in-context learning in a bit more detail in the second lecture, so this will be important. Next point relates specifically to the projects that you will be doing at the end, where the goal is that the student can interpret and critically analyze and judge scientific publications and apply and develop large language models via various API calls into their own code. All right, so that's sort of the formalities. The philosophy of these lectures is the following. There's a lot going on in this field, and there has been a lot going on. So I will not be covering everything. Even in this text vision domain, there has been research for the last 20 years. So I will be covering a lot of recent developments and not be diving too much into the history of those, which I definitely would recommend doing. But this course is sort of meant to give you an overview of what's currently happening and an opportunity to dive into this domain. What I will be showing is, that's why it's not a complete enumeration, but just some ideas. And my goal of this lecture is to provide you this overview. And I've succeeded if you will think after this lecture that combining self-supervised or vision language learning is exciting, and you might have some ideas on what to do in this domain. And of course, a note is that I'll be offering some master's projects in this direction later this year. As I've also said in the lecture, the next lecture is 25th April. Tutorial is after the lecture. And then for the projects, there's one common meeting and the rest of the meetings will be done on demand. All right, so we'll start with a review of self-supervised learning that we had also briefly covered in Deep Learning 1. So the goal of self-supervised learning is to answer this question: how can we learn without labels? And more specifically, how can we learn deep neural networks without labels? The answer is that we need to generate a loss that provides gradients, and that's all we need, right? And then we have our backprop technique and can throw optimizers at it. And of course, a data set. Right, and so here we'll now focus on signals that come from assuming every image is unique and assuming that if you augment an image, it stays invariant, the meaning stays invariant. So this is also commonly called as contrastive or noise contrastive learning. And we will briefly take another look at image reconstruction, masked image modeling. Right, so modern noise contrastive self-supervised learning sort of became popular after this work, non-parametric instance discrimination. But even before that, there was a work called exemplar CNNs, which basically introduced this idea of treating every image as its own class. Now, SimClear has the following figure where you basically take a single image and you augment it twice. So in this case, we're showing a badge with 2 different images, and each image is augmented twice. So overall, the badge contains, let's say, now 4 images. So we start with these 4 images and we throw them through the neural network. Now we get these embeddings from Z1 to Z4, but we know that the images 1 and 2 are the same and the images 3 and 4 are the same, right? Because they came from the same source image. They're just augmentations of each other. The step 2 is that you now compute the similarities of all the items in the batch, and you can simply compute this, for example, by normalizing these vectors and then computing the dot product. And this is the same as the cosine similarity. I mean, you could be using the L2 distance, but this is much cleaner. And if you have normalized vectors, the cosine similarity is simply the angle that's in between these vectors that lie on the unit sphere. And there's this parameter tau, which is basically a way to scale the inputs and widen the range of the cosine similarity. So cosine similarity obviously is just between 0 and 1. It's a -1 and 1. And then if you divide it by 0.1, it will scale it between -10 and 10. And then step 3, which is almost the last step, is you have now computed this pairwise cosine similarity. So now you have this matrix of batch size times batch size. And now what all you need to do is to relatively increase the similarity of the pairs and decrease the similarity of the non-pairs. So we call these positives and negatives. So increase the similarity of the positive pairs and decrease the similarity of the negative pairs. But keep in mind, I say relative because I ask you, what would happen if you were to only increase the diagonal elements, or in this case, only increase the elements of the pairs, for example? Yeah, so this wouldn't work because it could easily just predict everything as a 0 vector. That would solve the simple case of, then of course the diagonal elements would also be 1, but everything else would also be 1. So that's not quite what you want. And that's why you have in SimClear this sort of loss function. You recognize the similarities that I describe here, and the parameter tau is again the temperature. And you see here now the form of a softmax. And this is how we do this. So this, you see the softmax here. This is also called a non-parametric softmax because in this case, it's a softmax function. So all the entries are compared relatively, but you can do this comparison. For example, if your batch size is 16,000, this comparison is done against 16,000 other items, but you don't need a fully connected layer that's something times 16,000 big, right? So the embeddings could only be of size 128. But if your batch size is big enough, this softmax will be trying to discriminate between 16,000 instances. So this is like a useful concept to keep in mind that is very has been used for all kinds of directions. And so what SimClear does, or contrastive works generally do, is it enforces image uniqueness and enforces augmentation invariance. All right, I'm going to move quickly here because it's a recording and obviously you cannot ask questions here, but feel free to ask questions in the next lecture. All right, so language modeling. So, oh my God, the volcano is erudite. So why is this even a joke? Is sort of the question that language modeling is solving. So why is erudite not a good guess? So if you see this context, so if you see these words that are already there, the word erudite being what is meant is quite unlikely. And how can we now quantify this? Well, we say, okay, the probability of a data point, in this case, a data point is a whole sentence with words 1 to word n, can be decomposed as the probability of word 1 times probability of word 2 given word 1, and then times the probability of word 3 given probability 1 and 2, and so on and so forth. And you can obviously write that in a bit nicer way by using the product formulation. And so, as I've said, if we have this context, so the previous words, and we want to calculate the probability of the next word, all we need to do is combine all of these probabilities. So if we, for example, look at the probability of the word erudite coming, well, I mean, this is not a probability, but for a frequentist, this would be good enough. So how many samples do we have on the whole internet of, oh my God, the volcano is erudite? That's 600K. And oh my God, the volcano is erupting. It's like 3 million if you type it into Google. If you do this for all of the things, then you might get a rough estimate of what the language modeling objective is. It's trying to figure out what's the probability of each thing coming after the context. And obviously, this is not a particularly scalable way of doing it. And in this case, erudite is also a bit biased because of this webcomic that I've shown you, but I hope you get the idea. So let's take a bit of a closer look at the GPT model family. It simply does this via language modeling with a transformer that we've covered already. Here you can see that instead of words, we have you, and instead of, and we have now this parameter theta. Theta just represents all the neural network parameters. And you can see this u given ui minus k dot 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 until ui minus 1. So you can see that we have k items here. So k is the context length in this case. So we have a fixed length here that we're considering, or not a fixed length, but in this case, the length is k, and we're trying to predict the word that comes for the next UI for at the position I. And they're not words at this point, but tokens. And tokens means, okay, we're dealing with within the language model space. Right, so here's some more details. So yeah, U are the context vectors and N are the number of layers. So you simply throw them through a couple of transformer blocks. And then at the very end, you have the softmax. And notice that, or in practice, you do this causally. So you're not going to mask, at least in these causal. So there's causal language models and non-causal language models. In this case, causal simply means that you mask it from left to right. So you're always trying to predict the next word. You could, of course, also predict a word given a sentence in the middle or like the previous word or something, which indeed has some applications. But always predicting the next word is nice because then you can do autoregressive generation. So if you always take the next word and then append that to what you already have, put it again in the language model, get the next word. That way you can write whole stories, write whole books, write whole captions, right? Which is nice. If you can only predict the previous word, you sort of need to know where to end. And then, yeah, it's not quite as controllable, for example. All right. Right, so GPT-1 had 117 million parameters and mostly used supervised fine-tuning afterwards. And GPT-2, as we know, that's sort of when GPT became bigger, had already a 40 gigabyte size training data set and still often used fine-tuning to perform tasks. Importantly, then GPT-3 came out, which had a huge training data set and had the ability to perform a lot of language tasks without additional tuning. So it launched as an API service, so we don't have access to the original weights. There's a couple of open source versions now available, and we're also going to talk about in the tutorial. All right, what do we mean by it's able to accomplish a couple of tasks without additional tuning? So as it says in the title, language models are few-shot learners. What this model can do is it can do few-shot learning inside a language model, so without further fine-tuning. So in this case, what we do is all of this blue stuff here, translate English to French, and then all of these examples, that's what we give to the language model. What we give to the language model, we simply call context. Well, yeah, this is sort of the, yeah, we call context basically. In this case, the context includes both the task description, so what we want the model to do, and some examples. And then finally, the prompt is simply the thing that we are asking the model to do. Few-shot learning, this is also called the query, and the examples are called the support set, right? And now this model can solve this better than if you don't provide any examples beforehand. So one emergent capability of large language models is this in context learning ability, where here the task is defined inside the model's context, and the model picks up the task and solves it for a given sample. And this both, like, it does both of this during a single forward pass. but we're going to talk about in-context learning in a lot more details later. Just to compare it to usual few-shot learning, for example, in computer vision, so you know the terminology a bit better. If you're classifying between n classes, it's called n-way, like as if you have n ways to decide. And if you have k examples, you call these, each example is a shot. So for example, 5-way, 5-shot problem. Right. And previous methods, often rely on training explicitly for this objective. So, I mean, all GPT-3 did was predict for the next word. And this sort of ability came out of it, which is the surprising fact. Of course, there's some few shot-like items in the training data, but still, that this emerges is quite consistent and quite strong, even for tasks that are sort of way more rare. And you can see a bunch of examples in the paper and on the internet. And this is sort of the main learning, the main curve. So here you can see, first of all the way to the left, you can see the performance when you do 0 shots. So that's just when you ask, basically, translate English to French, cheese. And then the model outputs something. Already, you can see that the bigger model here, given in blue, already works better than the smaller models. But now if you keep adding examples, so if you give it one example, that's 1 shot, or if you give it a bunch more example, that's the few shot scenario, you can see that the curves for all the models actually keep on improving. But notably for the bigger models, they keep improving much quicker. So already at, what is it, maybe 20, 30 tokens, 100 tokens maybe, or 100 examples in the context, the largest GPT model is benefiting a lot from the context and is working a lot better. Right. One question I got here in the original lecture is why it's called in-context learning if no learning is happening. Learning isn't happening in the sense that weights are updated, right? You could, well, one reason why we call it in-context learning, I would say, is because you can see these curves. With more examples, it performs better. This is sort of typical learning like. What you could also say is that the learning is happening within the transformer between the layers, for example. That in the first couple of layers, it might have no clue. And with each more transformations, it's picking this up. Of course, no parameters are changed, but the states inside the transformer that go from layer to layer are, of course, changed. So these are, in a way, learning, you could say. All right, and yes, there's a short note about this, that GPT-3, well, ChatGPT not being all too different from GPT-3, except that you now use some human preferences to train GPT-3 to provide answers that we prefer. Then GPT-4, here's all the details we know. All right, that's pretty much it. There's some estimates that it's likely somewhere between 500 billion and 1 trillion parameters, but we don't know pretty much. And their paper only shows some results, which are of course great. But in this lecture, we are a bit more interested in actually how we can do stuff. So that's all we're going to do for GPT-4. I wish to highlight that there's a lot more to language models. There was a lot of stuff before GPT came out. There's a lot of stuff that's concurrent and that works better. For example, the Llama model, which has been even released open source, which is huge for the academic community. And even very, very large models have been released here. So we can use these, we can even fine tune these models. On how to fine tune large models, we're going to be talking about that in the second lecture. But just to let you know, there's a lot of different language models, some language models that have been trained on code, some that have been trained on Stack Overflow, all of these kinds of things. So I'm not covering them here, but just to give you some inspiration. And in the tutorial, you will be also learning how to use a Hugging Face library. So that will also give you access to a lot of these. Right. So one note here is this comparison to masked image modeling that we had in Deep Learning 1 as a self-supervised learning technique, where, of course, the task was to predict simply the RGB pixel values of the masked image. Now, something to think about would be that compared to, for example, the GPT objective, there's a difference, right? That words represent sort of the atoms of masked language modeling and have individual meaning, but an individual patch, which could be like just a 8x8 patch in the background, which is dark green or something, doesn't have individual meaning. Yes. And of course, the output space of a language model is quite vast and extremely general, while the output of an image model is just pixels. So there's some works which have generalized this a bit more. But maybe before you looking that up, you can think about, okay, what is the difference? Like they're sort of doing the same. One is doing it for language, one is doing it for vision, but the language model seems to be able to do everything that we need language models to do. The vision model doesn't. And yeah, so just from these two very basic things, maybe you can have a think about that. All right, so now we're going to go to multimodal learning. As humans, we have a couple of sensory modalities. Of course, we can see, we can hear, we can smell, we can taste, we can touch. This is probably not exhaustive. We can sort of also feel how warm it is in a room. And when thinking more about deep learning, we treat vision differently than we treat text. So captions is also different. Right. And so what modalities does deep learning mostly deal with? Generally anything on the internet, everything that's not password protected, really. People would scrape everything. There's a sort of not very good Wild West still going on about making very large training data sets without getting consent that these data sets or these items are being used for training. That's a big reason why these large companies are not publishing their training data sets, because they might get sued. But yeah, what's inside the internet? Mostly images, text, right? And then, of course, not all the data sets are simply scraped from the internet. There's a bunch that have been constructed explicitly, for example, data sets for self-driving cars with LiDAR points and so on and so forth. When we talk about multiple modalities, there's, for example, videos, a classic one where we have the RGB pixel frames, where we have audio, and sometimes audio transcriptions. For example, if someone is speaking, you can use a system that automatically changes audio speech to text, and then you have this language or text modality. Image text, of course, is the one that we're going to be talking mostly here, which is typically images with captions or images without text. But image text can also be, for example, that you have a scan of a document and this document contains some sort of figure, like a typical paper would, as well as text that you recognize perhaps with OCR. So this is even broader than this. Right. What makes multimodal learning interesting? So one example I would say is that text can be like an augmentation or like a broader description of the image. So everything that's in the caption, you know from the image. But given the caption, you have a decent idea of how the image looks like. You don't know how dark the green is or whether there's any grass in the image, because that's not the main point. You don't know if the batter is left-handed or right-handed, but you have a very good idea of what's going on. Another reason why modalities are useful is that the meaning depends a lot or can depend a lot on using both modalities. For example, in the left, I'm showing this image from the Hateful Memes Challenge of Facebook, where they made a challenging data set where basically a model needs to understand both the visual modality and the textual modality in order to make sense whether this is hateful or not. In this case, you wouldn't understand the meaning by only seeing only image or only text, but you need to see both. Likewise, there might be a case for seeing and not hearing. If in this picture on the right, you might not know whether it's an emergency case if you're not hearing the sound. Right, and then text can also be very detailed, of course. And not only these very short captions, but you can have a whole narrative, for example, where people go through an image and let's see if this animates and like point out where they are. And so you can see this whole data set has like almost 1 million images with audio where someone is reading out what's happening and pointing out where they are with what's happening. So when they talk about the blue sky, they will point to the blue sky. And some of this data set also contains segmentation. So these data sets can be very detailed. But then the more detailed they are, the smaller they are, because it requires human supervision, which is quite expensive. All right, but this is not the main reason. The main reason why vision language learning is useful is because of this language part, because the language part is a really universal format for posing and solving tasks, and is very much understandable, is the understandable way for us. And finally, we have these amazing capabilities of language models. So by connecting these with the vision modality, we want to get the benefits from these language models. All right, so the first thing that we've had, also briefly covered in Deep Learning 1, is going from SimClear to Clip, where Clip, instead of using an augmentation of an image, it simply uses image caption. And the magic, of course, lies in the training data and the scale. So Clip was trained in using 400 million image text pairs that were fairly clean, at least we assume, because the models that were obtained were really, or are really good and actually are available. Right, but also, and then it was able to do zero-shot image-to-text learning, which I'll talk about in a bit. But also, just as a caveat, this is nothing new. This has been done as early as 2016 with models that don't work as well. But just a reminder that everything I present is mostly not the first people that have done it, but some of these are the ones that make it work really well. So what you can do with Clip, and for example, there's this demo collab notebook, I'll be adding some more links in these slides, is you can input a bunch of images, you can input a bunch of text, and you can find out, okay, which image belongs to what kind of text. Or you can, as we've also done in our assignment last year, you can figure out which kind of attributes fit well to an image. So we call this zero shot because likely the model didn't really have had to classify cat, or like had a data set that had exactly this sort of description. You could be even more broader, saying like, is this image blue? Is this image red? Etc. And it could do zero-shot classification of any image you give it, right? Because all it tries to do is find which of these, let's say, 5 text embeddings is the closest to the image embedding you're giving it. All right. A note on what on like changing Clip a bit, basically, is this logged image tuning paper. The basic message is, okay, here you can see image and text. So these are the 2 encoders, and you're sort of mapping between those. So you can think about the inputs basically coming from the outer edges each. And what this paper shows is that you get better performance when you keep an image model frozen than if you train them both from scratch. So this is sort of different from Clip. Clip trains from scratch, the image encoder. But one caveat here is that they start with very good image encoders, okay? And they use a much not as clean of a training data set. So this is very important. So if your training data set for training this this contrastive loss, multimodal contrastive loss, isn't as good, then you're very likely to degrade the image encoder's performance. So you might as well keep it frozen, basically. Right, and if you keep the image encoder frozen, one big advantage is that you only need to extract the embeddings of the image encoder once, right? And after that, you can map them with an MLP or linear layer to this joint embedding space. But since the vision encoder isn't changing, you just get the forward passes once. So it's kind of nice. You can do this even with like huge models, like recently released 22 billion parameter vision transformer. So this is nice. I'm giving it this sort of token here at the bottom, which means like, okay, this is, you don't need that many GPUs to do something like this at the very least. I'm going to be talking about how much compute these sort of models use in the next slides as well. All right, next we're going to talk about the align model, which basically uses a very dirty training data sets to start with. Namely, it uses alt texts. Again, not the first one to do this, but it's important. So alt text is if you hover over an image, for example, and there's a text description where usually it's meant for visually impaired people or for systems that automatically output what is in the image, and also for search engines. But sometimes these captions can be very bad, like file London baud race to JPEG, or thumbnail for version as of 21. That doesn't really describe what's going on, right? So their innovation, they start with this very noisy data set and filter it on all kinds of ways. There's a couple more here actually that I didn't mention. The resulting data set size then is 1.8 billion image text pairs, and they use that to basically train in a clip-like manner. And they show that, okay, we get better or same performance as clip. Well, they use a lot more data, but they use more noisy data, so that's fine. And in this case, they use 1,000 TPUs, which is like GPUs, a bit more better than GPUs, with a huge batch size. What they can do is, of course, zero-shot classification, like we've done in clip. What they also show is image text retrieval, which is quite interesting. Well, which is also like clip, sorry, and similarly text image to text retrieval, also same as clip. What they also show is that you can do joint retrieval. So you take simply the, well, here is shown what you can do. You have the image of the Eiffel Tower plus the word snow, and then you get these sort of images back, which is nice, right? And how is this done? What you do is you get the vector of this image via the image encoder. You get this other vector of the word snow via the text encoder. And then you simply add these two vectors up. And then you find the images that are nearest in your database. So you've embedded all of your images in your database from the vision via the vision encoder, and then you simply get the nearest ones out. And likely this is something that Clip can also do because it's trained in the same way. Right. Just a brief note, what kind of text image retrieval data sets are out there. So for example, if we take Microsoft Coco, it has a bunch of captions, for example. And you can do image to text retrieval or text to image retrieval. And typically you would count, for example, given a number or given an image, how many correct captions can you retrieve? If you have a data set of captions, or if you have a text, how many of the correct images can you retrieve? All right, next, combining GPT or language models more broadly and X. So is GPT-3 an oracle? No, it's not. Do still people use it like an oracle? Yes, very much so. The reason is that language models contain factual knowledge inside its weights. So this is the benchmark called Trivial QA, which has questions like American calendar Pinckney's eponymously. Okay, I'm not going to read this, but basically it asks for factual knowledge inside. It asks for factual knowledge, and then the model needs to answer with something that it has learned, basically. So inside GPT-3 or inside language models, there's some knowledge. And using that knowledge will be useful for a bunch of other tasks, including vision tasks, right? So one paper, for example, from Menon and Vondrick, is where you can ask GPT-3 for useful visual features. So let's say you want to be able to recognize 1,000 different categories. So you ask GPT-3, what are useful features for distinguishing a golden retriever in a photo? And you provide this prompt. There are several useful visual features to tell there's a golden retriever in a photo. And this is all you have. This is the whole text. You send this to GPT-3, and then it outputs a list of features. And you use these features simply as the text that you give to a clip model. So for example, if you want to predict an airliner, you look for livery or paint scheme, you look for engines mounted on wings, you look for landing gear with wheels and tires, and you get all the similarities between these sort of very detailed visual descriptions and the image. And finally, you simply get the score by averaging the scores of these descriptors. And now you've sort of included a lot more details in doing zero-shot visual classification. Right. Another model that we're also going to talk about in the tutorial are Socratic models. So as we've seen now with this previous work, thanks to Clip being able to take in text input, we can now sort of have this model talk in quotation marks with a GPT-3 model or with a language model in general. So this work does a bunch of things. It basically uses language as a common language between models, between multimodal models. So if you have a audio to language model and you have a language model and you have a language to image model, then you can basically go all the way from audio to image if you wanted to. Right, so in this case, we're going to be looking at image captioning. So what you do first is you use Clip, then you use GPT-3, then you use Clip again. How do you do image captioning via these three tools? So all of these have not been trained for image captioning, right? But how can you solve it nevertheless? You first ask Clip, what kind of image type do we have? And there's only a few, right? There's a photograph, there's maybe a poster, there's a, I don't know, a sketch, there's a painting, and so on. It's much easier for a number of people. Let me give you the example. You give Clip five options. On this image, there's no person. On this image, there's one person. On this image, there's three. On this image, there's more than 4 people. You figure out via the similarities in joint embedding space which one is closest. Then you know, okay, there's 3 people in this. Okay, so you take this template and instead of num people, now you write 3 in there. And you do this for all these other things. So first of all, you need to have this sort of dictionary that you know. For number of people, it's the easiest. For objects, you take objects that you care about. All right, and then you filled out all the green stuff in this template. Now you have this template and you provide this template to GPT-3 and you're not gonna get a caption because the last thing it says is a creative short caption I can generate to describe this image is, and then you get a caption. And note that for all these language models, they are probabilistic, right? If you don't take the argmax always, but instead if you sample the next word via some temperature that's non-zero, then you can get multiple captions out. And then if you have those multiple captions, you can pick the one which Clip prefers, given the image. Now you could have also stopped at the previous step and just taken the one caption that's the argmax, but I think they showed that this performs a bit better. So for example, it gives you this sort of quite nice description. This shows an inviting dining place with plenty of natural light. Instead of this whole thing, there are no people on this image. This is likely taken in a room or a cabin or a hut. And yeah, so you get the advantage of that. However, note here in this very generic comment that we don't know whether GPT-3 might not have seen exactly this caption, right, word for word, or in this case, I think they test exactly for that as well, but we don't know what exactly GPT-3 was trained on. So there's somewhat of a caveat here, right? More on combining and calling language model APIs in the tutorial. Yeah, how will you use these models to make something new, or other models, of course. All right, so we've talked about language models now, we've talked about image models, we've talked about aligning image and text via some joint embedding space, but there's also other pre-training or other training methods. In this case, you might know this thing that you can take an image and you caption it. And for example, found this here. Yeah, I still wish we'd gotten a pool instead of this ridiculous sculpture, which is sort of an unexpected caption here, but okay. All right, captioning. Captioning is another way how you can train. there's this word called clipcap, called clip prefix for image captioning, and it's pretty simple to describe. You take clips, visual feature encoder, you get your visual features out, that's the blue points, and then you map them. This could be, for example, simply a linear layer or an MLP. You map them to the language space of GPT-2. So GPT-2 has, of course, these words or bytes or tokens. So GPT-2 maps words essentially first to a language space, which is 700 dimensional. And then the transformer does its thing. But this first mapping, this sort of dictionary, is a one-hot thing. We don't want to map an image to individual words at this stage yet. So what we do instead is we map the image features into this 700 dimensional space. And at this stage, we can throw them in with the same vectors that come from language. Right, so what this means now is that you take clip's visual outputs, you transform them into the language space, and you train the mapping network in such a manner that out of this model, you can get a caption out. So GPT-2 can be kept frozen or can be adapted, and it's trained for captioning. One thing here is that if you use a transformer, so if this mapping network is more complex, you can keep GPT-2 frozen and it works decently. And sort of here, I want to introduce the concept of a visual language model. And yeah, this was trained for just 80 hours on a single GPU, which is nice. All right, vision language models versus visual language model, or some people also call it encoder versus encoder-decoder architectures. So on the left, we can see CLIP, which projects these two into this joint embedding space. And you can do retrieval tasks, you can do zero-shot classification, which is great. There's this other family of models where this was the first example of it, where we call them visual language models. I mean, there's no one defining all of these, but visual language model makes a lot of sense. So for example, when the text decoder is a frozen language model, you map the image into this language space such that the decoder can deal with it. And note here, there's this dotted line. You can also include the text caption such that you somewhere get this joint embedding, because you might want to still be doing image text retrieval, and joint embeddings are quite useful for multimodal tasks and so on, right? But then you need to be careful if you put in the caption and then you predict the caption. Well, it could simply learn an identity, right? So you need to be careful that you always mask it in a causal manner, and that, yeah, we'll go to that in a bit more detail. At this stage, a quick quiz. So given the CLIP cap architecture, one question: why didn't they use GPT-3? Is it one, because the sparse attention in GPT-3 would lead to only looking at parts of the image? GPT-2 does the captioning job well enough, so no need for GPT-3. Or 3, it wouldn't work. You can think about it, you can pause it if you like. The answer is 3, because GPT-3 is only available as an API. You cannot backprop through it. You can get text output, but you cannot get gradients out of it. So in this case, because you're training the mapping network, you wouldn't be able to get gradients. Question number 2, why is the transformer adaptation and freezing of GPT-2 variant nice? 1, there's no catastrophic forgetting in the language model. 2, the language model can be made very efficient. 3, transformers are faster than fully connected layers. And 4, the number of parameters doesn't depend on the number of clips visual output size. Again, you can pause here if you like. Of course, transformers are slower than fully connected layers. I mean, they include fully connected layers in there. And yes, indeed, language models can be made very efficient. And indeed, there's no catastrophic forgetting in the language model if you indeed keep it frozen. And some other models also report that if you keep the language models frozen, it will generalize much better to new tasks at a later stage. All right. Next work we're going to be covering is the COCA work called contrastive caption. It's our image text foundation models. And this is now exactly the sort of architecture that I've talked about, which can also do captioning, and is a visual language model. All right, so how does it work? First of all, it learns the contrastive laws, just like CLIP. But then it uses those image embeddings to train a captioning model. And it trains this captioning model in this autoregressive manner. Yeah, so first of all, we have this clip-like contrastive aligning of CLS tokens, and then this autoregressive decoding. So autoregressive because we start with a start token, and then this needs to get mapped to the first word, and then this first sampled word needs to get mapped to the second word, etc., etc. So this is the task. This is autoregressive caption generation. So we have both a discriminative task via the noise contrastive laws and the generative task via captioning laws. And you can actually train this in a more efficient manner than simply doing multiple forward passes through the language text decoder. What you can do with such a model, well, you can scale it as they of course always do, and they scale it, they do. They train with a 3 billion data set, which has label names and paired text, and they also use this 2 billion sized align data set, and they train for 5 days on 2000 TPU V4, so that's even better than V3 chips. Yeah, so that's a lot. Anyways, so you can apply them in a couple of ways. Like obviously, you can use the image encoder now for classification. You can use the cross-modal things, just like you can use CLIP. But now you can also do image captioning. So yeah, bigger, better is sort of what you can see for the visual encoder. You can generate captions that look quite decent. Right, what else can you do? You can do, for example, multimodal understanding tasks. So what are multimodal understanding tasks? It's kind of like this hateful memes thing. You need both modalities to be able to answer this, right? The animations are a bit off here, but let's start at the left. So you have these images, and then there's this question, which object in this image is most related to entertainment? And then, okay, you need to look at the image and figure out it's TV. One note here is that this original VQA dataset was a bit easy because which objects are even related to entertainment? There's not that many. So even if you had a language-only model, you could solve this dataset quite well. So that's why they introduced then the VQA V2 dataset, which has balanced images to each question. So for example, if the question is the umbrella upside down? Then they have in this dataset, they have a yes image and a no image. And that's why if you train it with a language model, the best solution it could come up with would be guessing. So indeed, the model needs to look at the image. All right. So how does this work? How can COCA, for example, solve VQA? Or yeah, let's say, the first way is to do it in an open-ended manner, where you encode both the question and the image, and then you throw it into the text decoder, and then you ask it to provide a caption or provide a text output, it should say, and then you compare it to the true text output. Or you can simply do it in a discriminative setting, which is I think what they did here. Yes, what they did here, where they simply train a linear layer on top of a frozen model to predict one of the in a 3000 way manner. So if your data set has, for example, 3000 potential answers, then you simply train a linear layer to predict one of the 3000 answers, and then you compare, okay, was this correct or not? The open-ended one is, of course, more difficult. Right. Next model we'll be talking about is the BLIP paper, Bootstrapping Language Image Pre-training for Unified Vision Language Understanding and Generation. All right, and at the same time, we're going to be using this as a sort of practice to understand methodological figures in an easy easy way. All right, so what we can see here at first, and this is only part of the main figure, but we can see first there's the image encoder. We can see this typical transformer block. We can see this image has been patchified. All right, so what we know here is the image encoder is a VIT. Moreover, they use a pre-trained VIT, and they also use a pre-trained BERT to start with. BERT is a language model. And then they have this ITC. So what is this ITC? ITC here stands for image text contrastive learning. All right, so we have the caption, we encode that in the text encoder, add the CLS token, and map these CLS tokens together. All right, so that's exactly like CLIP, right? That's great, we know this. Then comes the second part. All right, so okay, next, okay, we have these language models. They look exactly the same as this other language model that we used for the CLIP part. And in fact, they are shared where they are, and where it says it's the same block, these things are basically shared, so same parameters. Now we have these two other models, other losses. So one is called ITM, image text binary matching, which simply, does this caption belong to this image or not? And I think they use hard negatives for that. So they make it slightly more difficult. But then in addition, they have this language modeling objective, which is simply this autoregressive captioning that we've already had. And that way you can sort of understand this thing that this model is doing. It's basically doing everything, right? It's trying to, similar to COCA, but it also has this ITM, which simply gives you a yes/no answer. All right, and it has in addition, that's why the paper is called bootstrapping. It has this iterative data filtering and data set expansion strategy, where they first train on a really clean data set, and then they can generate synthetic captions via the language model. These synthetic captions, you can again sample with a higher temperature, so you get quite some variance out of it. And then you can use this ITM, whether the image matches the caption, and the ITC model as filtering. So are the captions now good or are they bad? And that's how you can gradually expand your data set and filter your data set. Expand by captions, filter by checking whether something fits, it goes together or not. And they show that diverse captions help. All right. They have various usage modes. I think I've already explained. Well, one of them is, of course, the captioning. You can also use them in a bunch of other ways. So for example, for VQA, and we're going to be looking at them in the next slide. All right, so there's this data set called VisDial. So for example, VisDial stands for visual dialogue, where you have an image and text, and then given the dialogue history, you need to be able to answer basically. So as you can see, the last part of the dialogue is, what kind of dog is it? Looks like a beautiful pit bull mix. And then what color is it? So you need to understand both what we're talking about from the conversation and the image. And in this case, what they do is they turn this into a discriminative task, as we've also seen here. So what they do is they encode the image, they encode all of the chat history, so to say, as well as the question. And then they simply encode all of the possible answers and pick the one which is true, I think. Yes. For this other, there's another task which requires multimodal understanding called NLVR2. For example, where you have these two images of dogs, where it says the left image contains twice the number of dogs as the right image, and at least 2 dogs in total are standing. So you really need to, it's about comparing 2 images, and you really need to understand something, in quotation marks. And what they do here is they train cross-attention layers. So in this case, they do fine-tuning to be able to solve this task. All right, so last part of this lecture, we're going to be talking, I think, maybe it's the last part. Yeah, I think so. Talking about extending the context and emergence. And we're going to be talking about some, other ways of, or like what you can do more. Right, so first of all, this fromage model. Fromage, good abbreviation, stands for Frozen Retrieval over Multimodal Data for Autoregressive Generation. This is a reminder that catchy names matter, just because there's so much going on, right? All right, so the Fromage model is trained first of all with captioning, just like ClipCap. And you can see here, okay, at the very left, you have an image and you have a caption, and you have, if you go to the right, there's a generated text, which contains sort of this caption, and this is supposed to be captioning the model. All right. The date, and then the question is, okay, if this is a captioning loss, why are there two images next to each other? It's because they do this sort of data length augmentation. So with 50% probability, they concatenate two samples, which already looks a bit more like your data set is more mixed, more like a chat history, basically. But okay, they show that this helps for things, and we'll go into why this might be helping in a bit later. And then they, in addition, have this image text retrieval or contrastive loss. So this is kind of like the image text contrastive loss. And what they do is they append a new token, which they call the red token, at the end of a caption. And then, so it's kind of like a CLS token, but it's not. It's a red token here. It goes through the language model, and then you take this embedding to be mapped close to the image embedding. So again, these green things here are linear layers. And yeah, you have this generated text via next token prediction. Is a cross entropy loss. That's a cross entropy loss for captioning, and the info NCE loss for this matching part. And what they do is they add this red token to the dictionary of the language model. So the language model can output a red token. And then this red token, I'll show how it can answer with an image in the next slide. The nice thing here is trained for 24 hours on one GPU. All right, so to make this point clearer about how to retrieve images. So we have this history, right? And we want to, and the model is now supposed to be able to answer with an image. Right, so we know the last part is, okay, something gets projected into this joint embedding space, and then you simply do image retrieval. So then you pick the closest image in your data set. So how can we achieve that? So we're asking this bot or this model basically to say, show me some pictures of these birds. How do we get the answer? So first of all, we're always giving something to the language model. So what is the context? So first of all, we change this image to be an image token, right? Like, so we use this joint embedding model, and now instead of having image, we have visual language, basically. So these image tokens, and we append in front of it user. That's just text, right? And then we can do something like user. What is a bird? All of this is simple language, and then we start with we encode all of this other history and so on and so forth. And then we put this into the language model. And then if the language model predicts a text token next, we can add it to the context and keep generating autoregressively some answers. Now, if this language model predicts this red token, which it was trained to do at the end of a caption, right? Because that's what it's supposed to do. And because it's part of the dictionary, if it does that, then we get the hidden representation that's just one layer before it returns the red token. So in this case, the red token, that's just a token, right? That's always the same, no matter which image we would be trying to get. But if you go one representation before that, that has all the context that comes from the chat history before it. So this token before that has the information about what kind of image we're trying to retrieve. And we take this representation before the last representation, basically. And this is the one that's projected into the joint embedding space and also trained to be projected into this space in a clip-like manner. And then you can now return the closest image. All right, and these would be some results that they present in the paper. You can also do something like visual storytelling. So remember, red is just part of the dictionary, basically. So you can do, this is my dog, this is it taking a bath, this is us by the lake, red, red, red. And then you push this through the model, and this is all just one context, right? And now you look at, okay, what are the images that would have been retrieved by the red tokens? And indeed, like it knows it is a dog from the first sentence, and all of these can be returned like that. You can do the same thing that we've had earlier, that you can do an image plusing some text concept, and a bunch of more examples. Yeah, maybe you can come up with new things that you could do here as well. Yeah, hopefully this gives you some inspiration. All right, so Blip 2. So this is an upgrade on the Blip architecture, going more into this chat-like thingy as well. So the first stage of Blip is they train of Blip 2 is they train like Blip with a frozen image encoder here. Training like Blip means, of course, this ITC, IM, and LM objective. So they are already producing captions, right? In this case, they use the frozen image encoder and a relatively small BERT model to do the captioning. That's their first stage. At the second stage, they take a large language model, and by large, it's more than 1 billion sized. And now they take this one stays frozen, and they train it for the captioning objective, or as they call vision to language generative learning. So the key idea is first to pre-train to align into the large language model space by only using a small BERT model. And then at the second stage, use a large language model. And they show that this two-stage approach works better. And yeah, so you can see the same things happening. And this is exactly done the way I've shown you earlier, where everything is projected into this language space. Image, that's just image tokens. Language, that's just language tokens, and so on. And all the model does is it answers by tokens. In this case, actually, the model cannot answer with images because it doesn't have this red token or something like it. Right. I would also like to mention Flamingo, which is a model that they also take frozen vision models, and they take a frozen language model. In this case, they take the chinchilla model, if I remember correctly, which had 80 billion parameters. But you can see there's parts which were trained from scratch, these pink parts. So these pink parts are interleaved. They come after the vision encoder, and they are interleaved in the language model. And these parts which are introduced in the language model, they are initialized such that they don't interfere with the language model at first, because obviously the language model already works and is quite well. If you simply introduce some randomly initialized stuff, that completely messes up the language model, and then it wouldn't train. So these things are first initialized in such a manner. And then let's look at the broader figure. Okay, so you can see you have in gray at the very bottom interleaved visual text data. So what you have here is you have dog image. This is a very cute dog. Cat image. This is and then needs to output the text. What kind of data set is this? It's first of all aligns 1.8 billion text image pairs, but also 43 million web pages, which includes less or equal than 5 images plus text. So you think of it as some Wikipedia page which has text and image, or like some personal blog or whatever. So the training data explicitly has this mixture of content, right? It has text tokens, image tokens, text tokens, image tokens. So that's a very important point here. And this model uses a perceiver, which is just a transformer architecture specific type, to produce a fixed context vision input size. And so they can also use very long videos, and they also train with videos. for this, and it gives very strong performance. You can evaluate it with like 32 shots in the end, and it performs quite well. All right. I'm staying at a high level here because we're going to be diving into multimodal few-shot learning in the next lecture. This is another model called Frozen. And what you can see here is that, okay, you have, again, this sort of multimodal context where you have an image and you have some text. Don't be fooled by the emojis. They're also just text, like letters, basically. And then you ask, okay, this person is like, and then you ask it to complete it. And it can do, for example, this. It can answer with emojis, but this is just text. Or it can answer with the right answer. For example, in the second row, we have, this was invented by Zacharias Janssen. This was invented by Thomas Edison. And then it asks who invented the airplane, basically. And it can answer that. So what is this? This is multimodal in context learning, right? So it picks up the idea of, okay, it's asking for the inventor, and it does this in the context. So the model is not updated at this stage. Of course, they say that also that these examples are cherry-picked, or they are selected, as they write. But yeah, the method itself, notably, is not trained to do in-context learning. They simply take a frozen language model. They train a vision encoder to predict the caption. As a language model, they use an autoregressive Roberta model, which is a type of BERT model, but that's it. All right, and yeah, analyzing and what exactly is and how we can do and how multimodal in-context learning works is part of the next lecture. So thanks for listening, and speak to you next time.